Am I audible?
Yes, sir.
So let us start because it is already 5:30. So let us have the other part of the course, that is Dirac Dirac notation and Heisenberg formalism. Earlier we have discussed total angular momentum, which is the sum of orbital angular momentum and spin angular momentum. And let us discuss spin angular momentum of a matter in a quantum mechanical world. So this expression, which is shown in the screen, we have derived in our earlier classes, that is J cap is equal to L cap plus S cap. Is it visible?
Yes, sir.
And your J cap is total angular momentum operator, L cap is orbital angular momentum operator, and S cap is spin angular momentum operator. And your L cap and J cap, you can see, are Hermitian operators with the components Jx cap, Jy cap, Jz cap, and L cap is having component Lx cap, Ly cap, and Lz cap. So we can say that S cap is also a Hermitian operator with components Sx cap, Sy cap, and Sz cap. So in component form, we can write Jx cap is equal to Lx cap plus Sx cap, Jy cap is equal to Ly cap plus Sy cap, and Jz cap is equal to Lz cap plus Sz cap. So given that J cap and L cap satisfy the commutation relation, so you can write Jx cap and Jy cap in commutator bracket will give you IH cross Jy cap, and the derivation is shown in the screen. And similarly, your Lx cap, Ly cap having in commutator bracket will give you your IH cross Lz cap. Jx cap, Jy cap will give you IH cross Jz cap. Lx cap, Ly cap give you IH cross Lz cap. Similarly, you can have your Jy cap, Jz cap will give you IH cross Jx cap, and Jz cap, Jx cap commutation relation will give you IH cross Jy cap. Similarly, your Ly cap, Lz cap in commutation bracket will give you IH cross Lx cap, and Lz cap, Lx cap in commutator bracket will give you IH cross Ly cap. So you can see that Xy will give you Z, Yz will give you X, and Zx will give you Y in both the cases, total angular momentum and orbital angular momentum. So it is a cyclic in nature. So it is the cyclic, you can see it as a X, Y, Z, cyclic, Y, Z, X, cyclic, Z, X, Y, cyclic. So we don't know that S cap looks like how X cap look like at this stage because you can see in the screen, but we do know that L cap can retain in a coordinate representation and also in terms of angular variable, your theta and phi, and S cap cannot. So why it cannot be represented in terms of theta and phi, we shall discuss. And your L cap, S cap are commutating operators. So with this condition, you can have your Sx cap, Sy cap is equal to IH cross Sz cap. Ss cap, Sy cap in commutation bracket will give you IH cross Sz cap. So similarly, your you can see in equation 14.5a, your Xy, then it will be Z, Yz, X, Sz, X, Y. And in vector notation, you can write S cap cross S cap, cross product of S cap with itself will give you IH cross S cap. So you can write in commutation bracket Si cap, Sj cap in commutation bracket will give you IH cross summation k is equal to 1 to 3 epsilon ij k Sk cap. And you can write your S cap square is equal to Sx cap square plus Sy cap square plus Sz cap square. and your S cap square SZ cap in commutation bracket will give you 0. So it is also true that in commutation bracket you can write S cap square comma Sx cap is equal to 0, and similarly with Sy it will also give you 0. However, Sx cap, Sy cap, Sz cap do not commute among themselves. So we choose the eigenkette of the spin angular momentum operator to be simultaneous eigenstates of S cap square and Sz square. So to write down the spin angular momentum operator for electrons, or rather any other spin particle like that of neutron or proton, we start with the result that the electron spin angular momentum in z direction has the value plus minus h cross by 2, and it is derived by Uhlenbeck and Goldsmith in 1925. So we are looking for an operator S cap for which Sz cap has the eigenvalue plus minus h cross by 2, and which satisfies the commutation rules. Clearly, there will be two eigenkettes, and if we label them as phi 1 state and phi 2 state and written in a ket bracket, we can write Sz cap, your phi 1 in ket is equal to h cross by 2 phi 1 in ket, and Sz cap phi 2 is equal to minus h cross by 2 phi 2. And your phi 1, phi 2 are eigenkettes of S cap square as shown in the screen. So since Sz cap is Hermitian and your phi 1, phi 2 states have distinct eigenvalues, your state phi 1 and phi 2 are orthogonal and form a complete set for a two-dimensional Hilbert space for the spin angular momentum of the electron. And they can be scaled to be normalized, and so we can write in bracket phi I is equal to del ij, where ij is equal to 1, 2. So using the spectral representation, Sz cap can be written as Sz cap is equal to h cross by 2, your phi 1 in ket and phi 1 in bra, minus same for phi 2 and phi 2. So this is the correct form of Sz cap. Here is SAQ, and you can have your spin angular momentum matrix for electron, because in Dirac formalism, an operator can be represented as a matrix, and so also the eigenstates. So for J is equal to half, your Jx is equal to half H cross in matrix 0, 1, 1, 0. Similarly, your Jy is equal to half H cross in matrix 0, minus I 0. And Jz cap is equal to half H cross, so 1, 0 and 0, minus 1 in a matrix form. And you can check yourself that the eigenvalues of Jz, so also Jx and Jy are plus minus H cross by 2. So if a measurement of Jz is made, or you can measure Jx or Jy, you would get plus H cross by 2 or minus H cross by 2. And the matrix Jx, Jy and Jz satisfy the commutation rules as shown in the screen. Xy will give you Z with a coefficient IH cross. So the matrix says Jx, Jy and Jz are an appropriate representation of electron spin angular momentum operator, and you can write the spin angular matrix of the electron Sx, Sy and Sz as Sx is equal to half O H cross in matrix 0, 1, 1, 0. Sy is equal to H cross by 2 or half H cross in matrix 0, minus I 0, and Sz can be written as H cross by 2, 1, 0, 0, minus 1 in matrix 4. And you can also write the matrix Sx is equal to H cross by 2 sigma x, Sy is equal to H cross by 2 sigma y, and Sz is equal to H cross by 2 sigma z, where sigma x, sigma y, sigma z are the popularly known as Pauli spin matrix. And sigma x is equal to 0, 1, 1, 0 in matrix form, sigma y is equal to 0, minus I 0 in matrix form, and sigma z is equal to in matrix 1, 0, 0, minus 1. So we can also now write the matrix for operator S square as S square is equal to 3 by 4 H cross square 1, 0, 0, 1. And you can write S cap square is in ket phi 1 is equal to 3 by 4 H cross square of the state vector phi 1. Similarly, your S cap square phi 2 is equal to 3 by 4 H cross square phi 2 state. If you have your S is equal to half, then S cap square phi I state is equal to S into S plus 1 H cross square phi I state, where I is equal to 1, 2, 1 or 2, 1 or 2. And similarly, Sz cap state vector phi I is equal to Sz H cross the state vector phi I, where I is equal to 1 and 2. 1 or 2. Where the values of Sz are, Sz is equal to minus S or S. So the angular momentum matrix were defined in the basis J, Mj, and for J is equal to half, the basis eigenkets are half and minus half and half and minus half. And you can notice that S square and Sz are diagonal in the basis, and therefore we'll have simultaneous eigenvectors. And the eigenvector of matrices S square and Sz can be determined as Coulomb vectors, and these will be simultaneous eigenvectors. Phi 1 and phi 2 vector of the operator S cap square and Sz cap. And the phi 1 and phi 2 states are so written in a matrix form. Phi 1 state can be written as 1 0 in a column matrix, and phi 2 0 1 a column matrix. And your phi 1 and phi 2 bra can be written as a row matrix. So phi 1 can be written as in a row matrix 1 0, and the phi 2 bra can be written in a row matrix 0 1. So your state written in a ket will be written as a column, and in a bra is written as a row matrix. And your eigenvectors phi 1 and phi 2 are a column matrix, are also referred as spin up and spin down states. So spin up and spin down states are written in a column matrix. If the z component of the spin angular momentum is measured for an electron in the state phi 1 state, and result obtained would be your h cross phi 2. And if the z component of spin angular momentum is measured for an electron in state phi 2, the result obtained would be minus h cross phi 2. And your plus h cross by 2 will represent a plus h cross and minus h cross by 2. And the states phi 1 and phi 2 are often represented as shown in the figure with a pop with a arrow directed upward, or a arrow directed downward in a ket, or a plus or minus in a ket. So spin off is represented by your arrow directed upward or a plus sign in a ket, and spin down is represented by arrow directed downward or a minus sign in the ket. And the wave function for electron has two spin angular momentum states. One is plus and another is minus. One is up and another is down. Spin up electron and spin down electron. And this one uses the formalism called the Pauli two-component spinor formalism introduced by Wolfgang Pauli in the year 1927. And in Pauli two-component formalism, you can have Pauli matrices, and phi be the general spin state of the electron in the space. You can write phi state as a linear combination of eigenkets up and down, a spin. So it is shown as it is can be represented as shown in the screen. Your phi can be represented as C1 spin up plus C2 spin down, or in a bracket spin up and spin down phi, and spin down and spin up in a bracket, or spin down of the state function in a bracket. And your phi state can be represented in a matrix form in a column matrix C1 and C2 as shown in the screen. And phi bra can be represented as a row matrix C1 star, C2 star in a row matrix. And it is called two-component spinor, designating the state phi in ket by J to show that it is a spinor. So you can write J as C1, J of C2, J of, and J dagger is equal to C1 star, J of dagger, C2 star, J down dagger. So the equivalent description is shown in the screen. And you can write your spin angular Z component of spin angular momentum Sz cap, expectation value of Sz cap is equal to h cross by 2 J dagger sigma Z J. And the expectation value of Sz is written in terms of spinors and Pauli spin matrix in a compact way as shown in the screen. Okay. and your SS cap can be written as h cross by 2 sigma x, sy cap is equal to h cross by 2 sigma y, and sz cap h cross by 2 sigma z, where sigma x, sigma y, and sigma z are Pauli spin matrices. And Pauli spin matrices anti-commute, and you can write sigma I, sigma j is equal to 0, where ij is equal to x, y, or z. And the trace of each Pauli matrix is equal to 0. You can see here the Pauli matrix. The trace is the diagonal elements, summation of diagonal elements, and you can see in this Pauli matrix as shown in the screen. Is it visible?
Yes, sir.
So you see for sigma x, your trace is equal to 0 plus 0 is equal to 1. For sigma y, 0 plus 0 is equal to 0. For sigma x, 0 plus 0 is equal to 0. For sigma y is equal to 0 plus 0 is equal to 0. And for sigma z, 1 plus for minus 1 is equal to 0. So the trace is equal to 0. Trace is the sum of the diagonal matrix. So the trace of Pauli spin matrix is 0. And you can also show that it is antisymmetric. Anti-commute. So the square of each Pauli matrix is the identity matrix. So sigma I square is equal to 1. The Pauli matrix follow the commutation rules as sigma x, sigma y in commutation bracket will give you 2y sigma z. Similarly, sigma y, sigma z commutation will give you 2y sigma x, and sigma z, sigma x commutation will give you 2y sigma y. And the electron wave function, if you discuss, the probability density of locating a quantum particle at a point x is defined through its wave function psi, as shown in the screen, where in ket x or the eigenket of x of the position vector operator is defined as x cap x state is equal to x x. So you have seen that to solve stationary state of Schrodinger equation, that is h cap E state is equal to E of E state, where h cap is typically a function of position and momentum operator. To determine psi E x, you can have your in bracket x and E. However, if the quantum particle is the electron, which also has spin angular momentum, the wave function psi would not define the spin angular momentum state of electron at x, which you could either spin up or spin down, or h cross by 2 or minus h cross by 2, irrespective of its location. So you cannot therefore determine, for example, the probability of locating the electron at x in the spin of state. So instead of representing the state of the electron at x by a single wave function psi, it makes more sense to represent the state by two functions, psi up and psi down, where your psi up defines the probability of locating the particle at the point x in the spin of state, that is with the z component of spin angular momentum h cross by 2, and psi down defines the probability of locating the particle at the point x in the spin down state, that is with z component of spin angular momentum. So now the electron is described by a two-component wave function in a coordinate basis. Therefore, you can see that the size of the Hilbert space for the electron is double of what it would have been if it had no spin degree of freedom. And the wave function at x can be written in spinor formalism as a two-component spinor. So you can write psi p is equal to psi up and psi down in a column matrix. And psi p is a two-component wave function with a 2 cross 1 matrix, different from scalar wave function, which is just a complex number. So in general, in 3 dimensions, you can write psi p is equal to psi up and psi down in a column matrix, and we denote the column vector by a spinor xi p as shown in the screen, which is psi up, and psi down, plus psi down, xi down. And your the integral shown in the screen is the probability of obtaining the spin of state of at x comma y comma z, and your integration psi down square d tau is the probability of obtaining the spin down state at x comma y comma z. So you correct it in your course material. The second one is spin down. So further, integration psi up square d tau plus psi down square d tau is equal to 1. So if the Hamiltonian for the electron depends on the position, momentum, and spin operator, the general stationary state Schrodinger equation of the electron is h cap psi p is equal to E psi, which is equal to h cap in row column matrix psi up, psi down, and which is equal to E multiplied by your column matrix psi up or psi down. And H cap in general is a 2 cross 2 matrix and can be written as H cap J P is equal to E J P. And the time dependent Schrodinger equation will be I H cross del by del T in column matrix psi up or psi down is equal to H cap in column matrix psi up and psi down. And your H cap is equal to minus H cross by twice M del square dot I plus VR, which is very similar to which we have obtained in your Schrodinger formulation of quantum mechanics. And your I is equal to I is a 2 cross 2 identity matrix, and the only interaction is Coulomb interaction V, and the Schrodinger equation is now modified to minus H cross square by twice M del square I plus V I whole multiplied by J operated over your J P is equal to E J P, where J P is a function of X, Y, and Z. And the Hamiltonian is a diagonal 2 cross 2 matrix and reduces to identical partial differential equations psi up and psi down. However, if spin orbit interaction is included in the Hamiltonian, then you have your H cap is equal to minus H cross square by twice M del square dot I plus V dot I plus alpha L cap dot S cap by RQ. So L cap and S cap dot product will give you LX cap, SX cap plus LY cap, SY cap plus LZ cap, SZ cap, which is nothing but H cross by 2 alpha X, LX cap, LX cap, H cross sigma alpha, sigma X by 2 plus LY cap, H cross by 2 sigma Y plus LZ cap, H cross by 2 sigma Z. And the Hamiltonian in this case is no longer diagonal, and we get two coupled partial differential equations for psi up and psi down. And you will learn the technique of solving such equations using perturbation theory in the next course. Then your magnetic moment. The angular momentum of an atom is measured using its magnetic moment. And your orbital magnetic moment, as you have studied in your classical mechanics class, that the magnetic moment due to a charge q of mass m moving in a circular path of radius r with a velocity v can be shown as in the screen. So the angular momentum L vector is directed perpendicular to the plane of the path, and we can write L cap is equal to m r cross b. So the cross product will be directed perpendicular to the plane where r cap and v, r vector and v cap vector are situated. So this is mv r k cap. So k cap is perpendicular to r cap and v cap, and it is a unit vector along in z direction. And this rotating charge constitutes a current I, which is q v by 2 pi r in amperes. And your magnetic moment mu of this current loop is product of current and the area of the loop. So mu can be written as Ia, which is QL by twice m. And mu by L is equal to Q by twice m. If the charge Q is positive, the angular momentum and magnetic moment points in the same direction and they are parallel. If Q is negative, the angular momentum and magnetic moment point in the opposite direction and anti-parallel. So you can write mu L vector is equal to Q by M L vector. And the subscript L on the magnetic moment indicates that we are talking about the magnetic moment due to a charge moving in an orbit, and L vector is its orbital angular momentum. And the interaction Hamiltonian H for the HL interaction for the magnetic moment mu in an external magnetic field B is just its potential energy and can be written as minus Q by M Lx Bx plus Ly By plus Lz Bz. And the force acting on the charge in the magnetic field can be written as F vector is equal to minus del U, which is equal to Q by 2M del L dot B. And the electron moving inside an atom will therefore have a magnetic moment mu L vector is equal to minus E by twice M L vector, and experience a force F vector is equal to minus E by twice M del L dot B. If the external magnetic field is in Z direction, so your B vector is equal to Bz k cap, then the potential energy of the electron U is equal to E Lz Bz by twice M, and the force acting on it is along Z direction. So you can write F is nearly equal to mu Z del Bz by del Z is equal to E by twice M Lz del Bz by del Z. And the quantum mechanical analog to the orbital angular momentum L is L cap, and we can write mu L cap is equal to minus E by twice M L cap. So Goldsmith and Uhlenbeck analyzed a large number of spectroscopic lines and found that the results could not be explained with the help of three quantum numbers L, N, L, and ML. The most familiar example is two closely spaced D1 and D2 lines in the spectrum of sodium lamp. If we analyzed with the three quantum numbers N, L, and ML, there should have been just a single line in the sodium spectrum corresponding to transition from 3p to 3s. To explain the observed spectroscopic data, Goldsmith and Uhlenbeck advanced the hypothesis according to which every electron rotates with an angular momentum h cross by 2, which is the spin angular momentum, and carries, in addition to its charge, a magnetic moment equal to Bohr magnetron, which is equal to E h cross by 2 me and expressed as mu b. This increasing angular momentum is not due to the rotation of the electron about its axis. The magnetic moment due to spin angular momentum is actually mu s vector is equal to minus g es by twice m, where g is equal to 2.0023 is the Landé g factor, and E is the electronic charge, and S is the spin angular momentum. So where mu s cap is equal to minus g E by twice m s cap. The z component of magnetic moment can have the value mu z is equal to minus g E h cross by 2 4m is equal to mu 0, and mu 0 is equal to minus mu 0, corresponding to the two eigenvalues of sz cap, which are h cross by 2 and minus h cross by 2 for spin up and spin down states of electron respectively, and the interaction Hamiltonian for the spin magnetic moment and external magnetic field can be written as minus mu s dot b vector. Then we shall discuss Stern-Gerlach experiment. This is there both in classical picture and quantum mechanical picture, and also we can discuss it in the light of Schrodinger's formalism. And let us have the other part of the story which we are discussing, that is your wave packet, Gaussian wave packet. Is the screen visible?
Yes, sir.
Yes, sir.
You can see a wave packet representing a wave function representing a wave packet is given by psi, which is a function of x comma t, which is equal to integration minus infinite to infinite b, which is a function of k multiplied by exponential I multiplied by kx minus omega t dk. So this equation represents a Gaussian wave packet if both your b is of the form b is equal to e to the power minus k0 square alpha. Okay. And you can see that b is a Gaussian function in the k space picked about the value k0 and alpha is some constant. So your psi, which is a function of x comma t, can be represented as minus integration minus infinite to infinite e to the power minus k0 square alpha multiplied by e to the power I kx minus omega t dk. So at time t is equal to 0, the wave function psi at x and t is equal to 0 is equal to psi x of the Gaussian wave packet is of the form psi is equal to integration minus infinite to infinite e to the power minus k0 square alpha multiplied by e to the power I kx dk. If you substitute to s as k minus k0, you can have your psi x is equal to e to the power I k0 x multiplied by integration minus infinite to infinite e to the power minus alpha multiplied by s square minus I sx by alpha ds, which is equal to e to the power I k0 s multiplied by e to the power minus x square by 4 alpha whole multiplied by integration minus infinite to infinite e to the power minus alpha q dq. So your q is equal to s minus ik by 2 alpha, and your integration minus infinite to infinite e to the power minus alpha q square dq is equal to root over of pi by alpha, and you can find it from the standard integral. And you can have your psi is equal to fx e to the power minus x square by 4 alpha, where fx is equal to root over of pi by alpha e to the power I k0 x, and this factor e to the power I k0 x is the phase factor, and your modulus of e to the power I k0 x is equal to 1, and fx square is equal to pi by alpha. So the square modulus of psi, which is a function of x, is given by psi x square is equal to pi by alpha e to the power minus x square by 2 alpha. And apart from the phase factor, e to the power I k0 x psi is a Gaussian function of x. And in the next class, we shall discuss the width of Gaussian wave packet in x space and in k space, and also in momentum, and we can discuss how the product of del x plus del px is greater or equal to h and leading to Heisenberg uncertainty principle. Okay, am I audible?
Yes, sir.
So thank
Yes,
you.
sir.
Thank you. Tomorrow at 6, because they are the class of Professor Ganeshwar Nath is at 5. So let us have it around 6 p.m. and we shall have thereafter.
Okay, sir. Thank you.
Thank you.